Right now, if you step outside on a dark night and look up, you can see another galaxy with your own eyes. Most people don't realize that. That faint, blurry spot in the sky isn't a star, it's the Andromeda Galaxy. It looks small only because it's extremely far away. In reality, Andromeda is so huge that our entire Milky Way galaxy fits inside it. That tiny blur in the sky is hiding a size your brain simply can't process, because your sense of scale is being fooled. What you see in the sky is not its real size. In this video, we're going to remove the distance and finally understand the true scale of the Andromeda Galaxy. If you're ready to go deeper into this mystery, hit that subscribe button, and together, let's drift into space. On a moonless night, far from cities, the sky stops being a ceiling and becomes an ocean. Most of it is familiar. Stars, constellations, the pale river of our Milky Way. But then, off to one side, something else appears. Not a star, not a planet, not even a clean shape, just a faint, misty smudge, like a breath on cold glass. And here's the unsettling part. That smudge is not inside our galaxy. It's an entire galaxy of its own, so large on the sky that it spans about 6 full moons end to end, and yet most of us have never seen it at all. This is where our story begins. Because if we can't even see a galaxy that big, what else are we misunderstanding about the true scale of the Milky Way? Picture this. We step outside into true darkness. No streetlights, no phone screens, no glowing windows. We let the silence settle. We let our eyes adjust. And slowly, the sky changes. It's not instant. The US National Park Service warns it can take about 15 to 30 minutes for our eyes to properly dark adapt. NASA's Night Sky Network says it can take up to 30 minutes for full dark adaptation. At first, we think we're seeing the sky, but really, the sky is teaching our eyes how to see, and when the darkness finally locks in, a strange thing happens. Between the familiar stars, a soft, elongated haze becomes possible to notice. The Andromeda Galaxy, visible to the unaided eye from a dark site. It doesn't look dramatic. It doesn't look like the images. It doesn't look like a spiral. It looks like a mistake in the darkness. A smudge. And that is the trap. Because the universe doesn't announce its scale with fireworks. Sometimes it whispers it. This smudge has been seen for a very long time. Long before galaxy meant anything. Long before telescopes. Long before we understood that the Milky Way is not the universe. It's just one island in a larger sea. In the 10th century, the astronomer Abd al-Rahman al-Sufi described Andromeda in his Book of the Fixed Stars as a little cloud. Encyclopedia Britannica notes it being mentioned around 965 CE. A cloud. That word matters, because a cloud is near. A cloud belongs to the local world, and for ancient observers that's what the sky was. Local. A dome, a sphere, a map, a place where lights were pinned. Mysterious, yes, but still part of one coherent layer above Earth. So they recorded the smudge, but they couldn't place it, and that created a deeper mystery. How can something be visible and still remain completely unknown? Here's where the story cracks open. When we look up, we trust what we see. But the human eye was not designed to measure galaxies. It was designed to keep us alive on the savannah, to notice motion in grass, to track faces, to judge distance across a few hundred meters. And at night, our eyes change modes. Color fades, detail collapses, sensitivity rises. That trade is ancient and biological. In darkness, we rely more on the eye's low-light sensors, built for contrast, not fine structure. So what happens when the object we're looking at is not a point of light, but a giant, diffuse glow spread across the sky? Then brightness becomes a deception, because what matters isn't just how bright an object is overall. What matters is how bright it is per patch of sky, its contrast against the background. And that is exactly where galaxies become invisible. Astronomers model this problem directly. whether an object rises above the human eye's contrast threshold against the glow of the night sky. So the galaxy isn't hiding because it's far, it's hiding because it's spread out, like fog, like smoke, like a stain of light so thin that our vision almost refuses to admit it exists. And that wasn't the only problem. Even under truly dark skies, there's a limit to how faint a star can be before it disappears to most human eyes, often around magnitude 6 to 6.5 for typical observers and conditions. But Andromeda isn't just faint, it's faint across a wide area, which means it can be there, and still not register as there. To understand this, we don't need a telescope. We need an everyday scene. Imagine our city at night, seen from a hill. Downtown is bright, dense, concentrated, obvious. But the suburbs stretch outward, dimmer, thinner, harder to notice. If we judge the city's size only by the brightest lights, we would swear the city ends early. We would miss most of it. That is exactly what our eyes do to Andromeda. We see the downtown, the bright central region. We miss the vast outskirts because the light is smeared too thin across the sky. And suddenly the smudge becomes a warning. Visibility is not size. Brightness can be a mask. NASA's Hubble team describes Andromeda as so large in our sky that it spans 6 times the apparent diameter of the full moon and can still be seen with the unaided eye from a dark site. 6 moons. Hold that in our mind for a moment. The moon dominates our nights. It feels huge. It feels close. It feels impossible to ignore. Andromeda spans a far larger swath of sky, and yet it feels like a ghost. This should be impossible, except our brains are wired to interpret brightness as importance. A bright object feels big. A faint object feels small. Astronomy punishes that instinct, because in the universe an object can be incomprehensibly vast and still appear like a fragile scratch of light. And once we realize this, the night sky changes, because the question becomes unavoidable. If a galaxy can hide in plain sight, what else is hiding in our definitions? Ancient observers weren't ignorant. They were trapped by the information the sky refused to give. From Earth, the stars look like they're painted on one surface. Depth is missing. Distance is missing. The universe gives us no built-in scale bar, so a smudge could be anything. A cloud of gas nearby. A cluster of faint stars inside the Milky Way. A defect in the air. A trick of human vision. Even centuries later, after telescopes arrived, the confusion persisted. The object was described through early telescopes by Simon Marius in 1612, an event ESA highlights in its historical notes. But seeing it didn't mean understanding it, because more detail doesn't automatically reveal distance. More detail can still be a beautiful lie. What we needed wasn't sharper vision. We needed a way to measure the abyss, but that method wouldn't arrive quickly, and that delay is part of the tension, because for hundreds of years, humanity stared at Andromeda and still didn't know what it was. That's when the real problem appeared. The universe can be visible and still remain beyond comprehension. A star is a point source. It concentrates light into a tiny spot. That's why even faint stars can sometimes punch through the sky glow. But a galaxy is not a point. It's an extended glow. Its light is diluted across a huge area. So even if the total light is substantial, the surface brightness, the light per patch of sky, can be low enough to vanish. This is why light pollution is so cruel to galaxies. Not because it steals beauty in some poetic way, but because it raises the background brightness and the contrast collapses. Human vision is a contrast detector. When the contrast drops below threshold, the object doesn't become dim. It becomes absent, and astronomy has put real mathematics and experiments behind this idea, modelling the contrast thresholds that govern naked eye visibility against the sky background. So when we fail to see Andromeda from our neighborhoods, that isn't a small loss. It's a statement. It's proof that our modern world can erase an entire galaxy from human experience. So what are we actually seeing? We are not seeing Andromeda. We are seeing the portion of Andromeda that survives the filters of biology and atmosphere. We are seeing what remains after, our eyes' sensitivity limits, the sky's natural glow, and the thin spread of light across a wide shape have already done their damage. We are seeing the galaxy's presence, not its full body. A hint, a signature, a cosmic fingerprint pressed lightly into the darkness. And this is why brightness hides true size in astronomy. Because what looks small may only be the brightest in a region, and what looks empty may be filled with structure too faint for human senses. NASA's description, 6 moons wide, forces us to accept that the object in our sky is not tiny at all. It's our perception that is tiny, and once we accept that, we can't unsee the implication. Now the story turns, because the smudge is not just a curiosity, it's a measurement problem, a scale problem, a Milky Way problem. If Andromeda spans 6 moons on our sky, and yet it's not part of our galaxy, then its real size must be staggering. But we can't feel that yet, not emotionally, not intuitively, because our minds still secretly think in kilometers, in cities, in continents, and the universe is about to shatter that frame, because the next step is distance, and distance is where intuition collapses. Because Andromeda isn't just far, it's far in a way that rewrites what the word far even means. So the smudge becomes a doorway, a quiet doorway, and the moment we step through it, the universe stops being a picture and becomes a scale that breaks the human mind. The smudge in the sky feels harmless, but it's carrying a secret, a number so large that language barely holds it, and once we say that number out loud, the Andromeda Galaxy will stop being a soft patch of mist and become something else entirely. Because the next question is unavoidable. How far away does something have to be to look small, even when it's 6 moons wide? And when we answer that, we won't just understand Andromeda. We'll begin to understand what scale really means inside the Milky Way and beyond. We can look at that faint smudge and pretend it's small, but the moment we ask the simplest question, how far away is it, our intuition starts to fracture. Because Andromeda isn't far in the way mountains are far. It isn't far in the way oceans are far. It is far in a way that makes our normal sense of distance feel childish. Astronomers place Andromeda at about 2.5 million light-years away, and the moment we say that number out loud, we feel the problem. We can repeat it, we can memorize it, but we can't hold it. Not emotionally, not in the body. So we do what humans always do when reality becomes too large. We shrink it, we turn it into a neat fact, and that's where the danger begins, because 2.5 million light-years is not a neat fact. It's a rupture in our worldview. A light-year is not time, it's distance. It's the length light travels in 1 year, because at cosmic scales, miles and kilometers become useless words. NASA puts it plainly. Light moves at about 186,000 miles per second, and in 1 year it covers about 5.88 trillion miles. Even that, 1 light year, already feels like an insult to human experience. So we translate it into something we can feel. If we tried to drive 1 light year at a steady highway speed, not stopping, not sleeping, we wouldn't arrive in a lifetime. We wouldn't arrive in 1,000 lifetimes. It would take over 11 million years. 1 light year. And Andromeda is 2.5 million of those. This is where everything changes, because now the smudge isn't just over there, it's separated from us by a distance so extreme that the universe itself has to invent a new language to describe it. And this creates a bigger problem. If distance is that large, then what are we actually seeing when we look at Andromeda? Here's the strange part. That distance means Andromeda is also a time machine, not a fantasy one, a real one, because light does not teleport, it travels. So when we see Andromeda, we are seeing it as it was about 2.5 million years ago, because that's how long its light takes to reach us. Now, we anchor that time to something human. 2.5 million years ago, our ancestors were stepping into the earliest chapters of human technology. The Smithsonian notes that the earliest known stone toolmaking developed by at least 2.6 million years ago. So while early humans were striking stone, learning for the first time how to reshape the world with their hands, a photon left Andromeda. It began its long, silent crossing, not through air, not through ocean, through vacuum, through the frozen dark between galaxies, and only now, only tonight, does it arrive at our eyes. That's what we're doing when we look up. We're not just seeing far, we're seeing deep, and yet we don't feel it, because our minds were never trained for this kind of truth. Imagine you're in a long hallway. At one end, someone turns on a flashlight for a single second and switches it off. You don't see it instantly, not because your eyes are slow, because the light has to cross the space between you. Now stretch that hallway until it becomes absurd. Stretch it until it leaves the Earth behind. Stretch it until it becomes the space between galaxies. That's Andromeda, a signal switched on long ago, and only now arriving. And when we truly accept that, the smudge stops being a smudge. It becomes a message from a time when no human cities existed, no writing, no empires, no recorded history, just early hands and raw stone under a sky that still held Andromeda in the same place. This should make us feel small, but it should also make us feel awake. For centuries, Andromeda was called a nebula, a cloudy thing, a nearby thing, a thing that might be inside our own Milky Way. And then the scientific world hit a wall, because scientists hate mysteries, but they hate measurement even more when it refuses to cooperate. In 1920, the question exploded into public view in what became known as the Great Debate about whether spiral nebulae were inside the Milky Way or were separate island universes. What came next didn't feel like poetry. It felt like accounting, careful, relentless, unromantic measurement. And the key was a certain kind of star, a star that pulses, a star that keeps time, a Cepheid variable. Henrietta Swan Leavitt, working with photographic plates at Harvard, uncovered a relationship between a Cepheids pulsation period and its true brightness. Work published in 1912 through Harvard College Observatory channels. That discovery meant something enormous. If we know how bright a Cepheid truly is, and we see how faint it looks from Earth, we can measure distance. Not guess it, measure it. NASA describes how Edwin Hubble's observation of a Cepheid known as V1 in Andromeda became a critical step in demonstrating Andromeda was far outside the Milky Way. This was the moment our universe cracked open, because once Andromeda was proven to be a separate galaxy, distance stopped being a philosophical argument. It became a number. And today, that number is still haunting in its simplicity, about 2.5 million light-years. Now, we face the next illusion. Distance doesn't just separate objects. Distance compresses them. It crushes them down into small angles in the sky. That's not a metaphor. That's geometry. A familiar example is almost too simple. A building nearby fills your vision. The same building miles away becomes a thin shape. Push it far enough, it becomes a dot. Andromeda is the cosmic version of that. It is an object so large that it contains hundreds of billions of stars in many estimates. Yet from Earth it becomes a quiet patch of haze. And here's what makes it emotionally unsettling. NASA notes, Andromeda is so close, astronomically speaking, that its angular size is about 6 times the apparent diameter of the full moon. 6 moons. And still, most of us have never truly seen it. Not because it's small, but because distance and faintness collaborate like a conspiracy. A vast object can be stretched across the sky and still feel like nothing. And this raises another question. If it's already that big on our sky, what does that imply about its true size? Let's translate the distance into a space we can walk through. ESA and NASA describe Andromeda's distance as roughly 2.5 million light-years, and NASA even frames it as roughly about 25 Milky Way diameters. So here's our scale model. If we shrink the Milky Way's disk to the width of a single room, then Andromeda is not across the street. It's not across town. It's dozens of rooms away, lined up end to end, and the space between is not filled with comforting emptiness. It's filled with thin gas, dark matter, faint stars, radiation, the quiet infrastructure of the local group. This is why the sky fools us, because the sky offers no depth cues. It gives us no near and far the way a landscape does. It flattens the universe into a dome, and our brain accepts the dome because it has to. Our survival never depended on imagining millions of light years. But our understanding does. If you hold your arm out and cover the moon with your thumbnail, it disappears. That feels normal. Now remember, Andromeda spans about 6 moons in apparent width, and yet, most of that width is too faint for your eyes to collect. So the galaxy is both enormous and invisible at the same time, and that contradiction is not a failure of the universe, it's a revelation about us. We don't see reality. We see what our biology allows. We see what contrast allows. We see what darkness allows. And that means the night sky isn't showing us what's there. It's showing us what survives the filters. And that is deeply unsettling, because it means even when we stare directly at the truth, we may still only be seeing a fraction. So now we have the distance. We have a unit that finally matches the scale. We have a measurement method rooted in real stars and real light, built by real people. Leavitt at Harvard, Hubble at the telescope, astronomers fighting over the scale of the universe until the evidence forced the answer. We have crossed a threshold, but we haven't solved the mystery. We've only opened the first door, because distance tells us how long the light travelled. Distance tells us how far away the island is. But distance does not tell us the island's true shoreline, and that's the next trap. Because the brighter centre is easy to see, the faint outskirts are not, and if brightness can hide distance, it can also hide size. So here's where the tension tightens. If Andromeda is 2.5 million light-years away, and still sprawls across our sky at 6 moons wide, then the real structure must be staggering. But that's not the whole story, because what we see is not the full galaxy. It's the part of the galaxy bright enough to survive the darkness and survive our eyes. Which means the next question isn't about distance anymore, it's about edges. And galaxies don't have edges the way we want them to. They fade, they dissolve, they vanish into black long before they truly end. So when we return to that smudge, we're going to ask something sharper, something more disturbing. How much of Andromeda is missing from our view, and how much of the universe is built the same way? Real, massive, and almost completely unseen. We think we've met Andromeda. We've seen the smudge. We've swallowed the distance, about 2.5 million light-years, and felt our intuition collapse under the weight of it. So we assume we understand what we're looking at. A galaxy, a spiral, a single object with a single size. But then the universe does what it always does. It adds one more twist, because the Andromeda we see is not the Andromeda that exists. What we see is the part that survives brightness. What exists is everything that doesn't. And that difference is where the real scale begins. From Earth, Andromeda can span a shocking amount of sky, about 6 times the apparent diameter of the full moon, and yet it still appears like a fragile blur, barely there. That contradiction is the warning. Because brightness has a strange power in astronomy, it makes us confuse what's bright with what's big. Our eyes and our brains treat the brightest region as the main body, the real thing, the part that matters. But galaxies don't work like that. A galaxy isn't a coin with a clean rim. It's a storm of stars and dust and faint, diluted light, spreading outward until it becomes indistinguishable from darkness. And in that darkness, a huge fraction of reality goes missing. Not because it isn't there, but because it's too thin for our senses to catch. Picture a city at night seen from far away. Downtown is obvious. Hard edges, bright cores, a concentrated blaze. But as you look outward, the city doesn't stop. It thins. Streetlights become scattered, neighborhoods dim. Then the lights begin to disappear one by one, not because the city ends, but because the lights fall below what your eyes can separate from the black. If you tried to measure the city's true size using only the brightest streets, you would be wrong. You would shrink the city into a glowing center and call it complete. That is exactly what happens with Andromeda. The bright inner disk is our downtown. But the galaxy extends far beyond that, into suburbs of starlight so faint they dissolve into the background. And this creates a bigger problem. If the galaxy fades instead of ending, where do we draw the line? Where does Andromeda stop? Out there, beyond the bright spiral glow, stars still orbit. They still exist. They still carry the history of the galaxy in their motion and their chemistry. But their light is spread out, diluted across enormous area. Astronomers call this idea surface brightness, how bright something is per patch of sky, not just in total. And here's the unsettling part. An object can be huge and even contain a tremendous amount of light overall, yet still be difficult to see because that light is smeared thin. NASA describes entire classes of galaxies that are so faint they can be fainter than the night sky itself, making them incredibly difficult to detect. That same principle haunts our view of Andromeda's outskirts, not because Andromeda is weak, but because the outer regions are diffuse, like fog, and fog is not defeated by distance alone. Fog is defeated by contrast. If the contrast isn't there, the fog becomes invisible, even when it's filling the entire street. So when the outer stars disappear, the galaxy has not ended. Our ability to extract it from darkness has ended, and that's when the real problem appears. If visibility depends on our tools, then the galaxy's size depends on our tools too. We want edges. We need edges. Edges make the world measurable. Edges make the world safe. A mountain has a boundary. A building has a wall. A continent has a coastline. But galaxies are not built for human comfort. They don't end like objects. They end like breath. They fade. They blur. They dissolve into the background of space, where faint stars and faint light don't announce themselves. That's why astronomers use operational definitions for size, definitions based on brightness thresholds and measurement conventions, because nature doesn't hand us a clean border. So when we ask, how big is Andromeda? We're not asking one question. We're asking several questions at once. How big is the bright part we can photograph easily? How big is the disk traced by faint stars? How big is the extended structure revealed only by deep surveys? And how big is the part that exists but still escapes detection? Every answer has a different edge, and every edge is in some way artificial, not false, but incomplete. This is where modern astronomy becomes almost unsettlingly human, because telescopes do not simply see better, they negotiate with darkness. They collect time, They build images out of patience. NASA's Hubble team describes a panoramic Andromeda mosaic that took over 10 years to assemble, requiring hundreds of overlapping snapshots stitched into one portrait. That fact alone should change how we imagine a photograph of a galaxy. We're not taking a picture like we take a picture of a face. We're gathering photons like rain in a bucket, drop after drop, until the invisible becomes barely visible. But even then, detection is not existence. Detection is a threshold, and thresholds create illusions. If our instrument can only detect light above a certain level, then anything below that level becomes not there in the final image, not because the universe removed it, because our method filtered it out. This is why deep imaging always feels like a reveal, not because the galaxy is changing, but because our ability to notice it is changing. When astronomers observe Andromeda across different wavelengths, and with deeper surveys, the galaxy's extent grows. NASA's SWIFT mission, observing Andromeda in ultraviolet, describes it as more than 220,000 light-years across. 220,000 light-years. We can say the number. But to feel it, we have to translate it. If a single light-year is the distance light travels in a year, already beyond any human journey, then 220,000 light-years is a span where the word across becomes almost absurd. It means light would take hundreds of thousands of years just to cross the galaxy's breadth. That's longer than all of recorded human history by orders of magnitude. It's longer than the entire rise and fall of ancient empires. It's a scale where our species becomes a brief flicker. And yet, even that number, 220,000, still isn't the final boundary of Andromeda's reality, because the faint outskirts, the low surface brightness regions, the extended structures, push beyond what a bright disk photo suggests. Astronomy.com describes work tracing Andromeda's extended disk out to a diameter around 220,000 light-years, emphasizing that it reaches far beyond the bright inner regions that dominate easy photographs. So the galaxy grows as we look deeper, and that should disturb us a little, because it means the size of a thing can depend on how long we stare at it. You've felt this in your own life, even if you've never studied a galaxy. When you walk into a dark room, at first you see nothing. Then shapes emerge: a chair, a doorframe, a window. Not because the room changed, but because your eyes gathered enough information to build reality. Now imagine that process stretched across a decade. That's what telescopes do with Andromeda. They don't reveal a static object all at once. They reveal it in layers, and each layer whispers the same unsettling truth. There is always more galaxy than we can see. So now we can name the mechanism. Brightness hides size because galaxies aren't uniform. They have dense cores, active star-forming lanes, bright clusters, regions that shout, and they have outskirts, thin, quiet, ancient populations of stars that barely glow against the sky. Those outskirts don't vanish with distance. They vanish because their light becomes comparable to the background. Astronomers studying visibility emphasize that detectability depends on contrast thresholds. What rises above the sky glow, and what sinks beneath it. So the bright inner disk becomes the galaxy in our mind, and the rest becomes nothing. But the rest is not nothing. The rest is mass, history, structure, and if we ignore it, we misunderstand the scale of galaxies, including our own Milky Way. This is why this chapter matters, because Andromeda is teaching us how perception fails, and if perception fails on a galaxy we can literally see with our eyes, then the Milky Way, where we are trapped inside the disk, will be even harder to understand. So we let go of the childish expectation of edges. We accept the uncomfortable version of reality. A galaxy is not a clean object. It is a gradient of starlight, a central blaze that thins outward into the invisible, and that changes the meaning of every image we've ever seen. A photo of Andromeda is not the galaxy. It's the galaxy above a threshold. It's the part that survived detection. It's a truth, but not the whole truth. And that realization sets a trap for us. If galaxies don't have sharp edges, and if brightness hides the outskirts, then measuring size is not straightforward. It becomes a battle between data and definition, between what our instruments can detect and what we know must still be there. So now we're standing at the edge of a question that doesn't have an edge. Andromeda grows as our methods deepen. Its apparent size can dwarf the moon in our sky. Its true extent stretches into regions where starlight becomes almost indistinguishable from the dark. And this creates the next mystery. How do we measure the size of a galaxy that fades instead of stopping? How do astronomers draw boundaries on something that behaves like mist, real, massive, and quietly dissolving into black? Because once we start trying to measure what has no clean border, we're forced into methods, into rules, into competing definitions, and that's where the story becomes even more unsettling, because the universe doesn't just test our imagination, it tests our measurements, and it doesn't care if we're ready. We keep saying it like it's simple. How big is a galaxy? As if a galaxy is a rock, as if we can wrap a tape measure around it and be done. But galaxies don't sit still. They don't have walls. They don't have edges we can point to and agree on. They fade into darkness and into our own uncertainty. And that means something unsettling. The size of Andromeda depends on what we choose to count and what we choose to ignore. We already know Andromeda is close in cosmic terms, about 2.5 million light-years away. We know it spreads across our sky like a ghost that shouldn't exist. But the moment we try to measure it, the galaxy turns into a moving target. Because size can mean different things. The bright disk we photograph easily, the faint outskirts that barely rise above the night sky, the extended regions traced by individual stars, the farthest reach where gravity still holds everything together. Each method makes Andromeda expand or shrink, not because the galaxy changes, because our definition changes. And that's when the real problem appears. If we can't agree on the size of a galaxy we can see, how confident are we about the true scale of the Milky Way, where we're trapped inside the structure itself? Imagine we're standing in thick fog at night. A streetlight glows nearby. We can see the bright core of it clearly, but the glow spreads outward, thinning, fading, dissolving into the mist. Now ask yourself, where does the light end? It doesn't. It just falls below what our eyes can separate from the dark. That's a galaxy, not a solid object, a gradient. And measuring a gradient means we have to choose a rule, a threshold, a definition. One of the oldest, most common approaches is brutally practical. Astronomers take an image and measure how the light fades with distance from the center, building a brightness profile. Then they pick a conventional cutoff, a faint shoreline where the galaxy's light becomes difficult to distinguish from the sky background. Caltech IPAC's NASA-supported extragalactic database explains that a widely used standard is an isophotral diameter, a boundary defined by a specific faint level of surface brightness, chosen historically because it was near the limits of detectability on older sky surveys. This is not arbitrary in a careless way. It's practical science. We can only measure what rises above noise. So we create a consistent rule, and we apply it across galaxies. But this creates tension immediately, because change the threshold, and the galaxy changes size, deepen the exposure, and the galaxy grows, improve the camera, and the edge moves outward. The border is not a property of Andromeda, it's a property of our measurement, and that isn't the only complication. Different wavelengths reveal different galaxies. Ultraviolet emphasizes young, hot stars. Infrared penetrates dust and highlights older populations. So when we measure size using light, we're also measuring which stars we've chosen to emphasize, and that means two astronomers, using two valid data sets, can produce two different diameters without either one being wrong. So astronomers do something more direct. They count stars, not metaphorically, literally. Andromeda is close enough that space telescopes can resolve its stars individually. NASA's Hubble surveys have done exactly this, assembling mosaics that contain images of 117 million stars in Andromeda's disk. That number is hard to feel, so we translate it. If we tried to verify those stars like a human clock, 1 per second, never sleeping, it would take more than 3 years just to count to 117 million. And that's not the whole galaxy. That's a mapped section, built from thousands of images from a telescope orbiting above the atmosphere, collecting light with patient precision. This method has a different kind of power, because even when the galaxy's glow becomes too faint to measure smoothly, stars still stand out, tiny points against black. So star counts can trace Andromeda farther into its outskirts than brightness profiles alone. The PHAT project, the Panchromatic Hubble Andromeda Treasury, was designed to resolve huge portions of Andromeda into individual stars across multiple wavelengths, precisely to study its structure and stellar populations with less ambiguity from blended light. But even star counts have limits. Dust hides stars. Crowding blends them together near the dense center. Foreground stars from the Milky Way contaminate the view, so the story becomes a careful balance: statistics, corrections, models, and uncertainty. And that uncertainty isn't a flaw. It's the honest fingerprint of measuring something so large it refuses to fit in our instruments. When light becomes unreliable, astronomers turn to something colder: motion. Because motion is evidence. Stars orbit, gas rotates, satellites move under gravitational control, and gravity does not care whether something glows. This is the logic Einstein gave us in the language of modern physics. Mass shapes motion, and motion reveals mass. So, astronomers measure how fast material moves at different distances from a galaxy's center, building what's known as a rotation curve. That curve doesn't just tell us the galaxy's speed, it tells us how far the galaxy's gravitational influence extends, how much mass is still holding on out there in the dark. Even without diving into dark matter yet, the key idea is simple. The galaxy is larger than its light, because gravity reaches beyond what we can see. This method is powerful, but it changes the meaning of size again. Now, we aren't measuring the bright disk. We aren't even measuring the faint stellar outskirts. We're measuring the realm where the galaxy still dominates motion, and that realm can stretch far beyond the visible structure. So the same object, Andromeda, can have multiple honest sizes depending on whether we define it by light, by stars, or by gravity. Here's the strange part. The disagreement isn't mostly about human error. It's about the universe refusing to be a simple object. Galaxies are layered systems, a bright central bulge, a sprawling disk, faint outskirts and extended structures, a gravitational domain that reaches into the dark, and every measurement method locks onto a different layer. Even Andromeda's orientation complicates the picture. NASA and ESA describe Andromeda as highly tilted relative to our view, seen almost edge-on in major Hubble mosaics. Tilt changes what light must pass through. It changes how we correct for dust. It changes how we infer shape from a projected image. So the diameter is never a simple line. It's always an inference. And the deeper we go, the more the story fractures into choices. We tend to treat science like certainty, but at the frontier, where galaxies fade into the sky background, uncertainty isn't failure. It's the terrain. Even Caltech IPAC's discussion of galaxy diameters makes this clear in practice. Some measures are straightforward, while others depend on models and assumptions about how light behaves at the faintest levels. And this is where the emotional weight lands. Because the most important parts of a galaxy, its true extent, its faint structure, its outskirts, live exactly where measurement becomes fragile, at the edge of detection, at the edge of definition, at the edge of what we can prove without making choices. And that means the universe forces us into humility. We don't measure galaxies like rulers measure wood. We measure galaxies the way sailors measure coastlines in fog, by agreed rules, by repeated passes, by better instruments, by better patience. You can feel this uncertainty in your own hands. If you've ever tried to draw the edge of a cloud on paper, you already know the truth. The cloud is real, but the border is something you invent so you can talk about it. That's what astronomers are doing, carefully, honestly, when they define where a galaxy ends. Not because they're guessing, because nature refuses to give a clean line. So what do we gain from all of this? We gain something more powerful than a single number. We gain a layered understanding. Brightness profiles give us consistent, comparable, photographic sizes across many galaxies. Star counts reveal structure where smooth light fades, turning the outskirts from guesswork into mapped reality. Motion shows us the galaxy's reach in gravity, where it still controls the dance of matter, a different kind of size entirely. And once we see this, Andromeda stops being a smudge and becomes a system, not an object, a living hierarchy of structure. And that matters because our video isn't really about Andromeda. It's about what Andromeda teaches us about the Milky Way. Now, we're ready for the next step. Because once we accept that a galaxy's size depends on method, one region becomes the most psychologically dangerous of all: the disk. The bright, star-filled city we tend to call the galaxy in everyday language. NASA's swift observations describe Andromeda as more than 220,000 light-years across, a number that already feels impossible to hold in the human mind. And yet, that number is only meaningful if we know what it refers to. What part of the galaxy? What definition? What threshold? So here's the cliffhanger that pulls us forward. If the disk alone spans hundreds of thousands of light-years, then the disk is not just a region. It's a city of stars so large that across becomes an emotional problem. And once we step into that city, once we map its scale and compare it to our own Milky Way, we'll finally feel what galactic size means in human terms. Because the next question isn't, how do we measure Andromeda? It's darker than that. It's, what kind of structure can survive at that scale and without collapsing into chaos? We can talk about halos, we can talk about dark matter, we can talk about edges that don't exist. But there's one region of a galaxy that feels brutally personal, the stellar disk, because the disk is where the light concentrates, where spiral arms carve patterns through time, where gas turns into new suns, where most of the galaxy we imagine actually lives. And here's the unsettling contradiction. Andromeda's disk is more than 220,000 light-years across. Our Milky Way's disk spans more than 100,000 light-years. So when we compare the two, we aren't comparing big and bigger. We're comparing two star cities so vast that even light, moving at the universe's speed limit, needs hundreds of thousands of years to cross one of them. And that's when the real problem appears. If the disk is the part we think we understand, why does it still feel impossible to picture? When astronomers say disk, they don't mean a flat solid plate. They mean a rotating, star-filled region, thick enough to hold dust, gas, star clusters, and entire spiral arms, yet thin compared to its width. A galaxy's disk is where the action is. Most of the gas and dust that fuels new star formation lives there. Most of the young, bright stellar populations live there. And even in Andromeda's ultraviolet portrait, NASA describes this contrast clearly. A smooth, redder central bulge, and beyond it a disk sparkling with hot, young blue stars. So the disk is not just a region, It's a living ecosystem of stellar ages, a place where time is written in colour. But then, the mystery deepens, because a disk that large shouldn't hold a recognisable pattern for long. Not with everything orbiting at different speeds, not with gravity constantly pulling and tearing, and yet spiral arms persist. Imagine a circular running track, like a school track. Now imagine everyone on that track is running, but not at the same speed. The runners on the inside lane move faster. The runners on the outer lane move slower. If someone tries to paint a perfect spiral stripe across that moving crowd, that stripe should twist tighter and tighter until it becomes a mess. That's the winding problem in plain human terms. Galactic disks rotate differentially. Inner regions orbit faster than outer regions. So if spiral arms were just material made of the same stars and gas, those arms should wind up and dissolve. But they don't. And that's where the story cracks open. Because spiral arms are not just decoration, they're evidence that something deeper is shaping the disk. Let's face the numbers without letting them turn into empty trivia. NASA's swift observations describe Andromeda as more than 220,000 light-years across. That's the scale of the disk-like structure we can trace in detail across wavelengths. Now compare that to the Milky Way. NASA describes our home galaxy as a spiral with a disk of stars spanning more than 100,000 light-years. So Andromeda's disk is roughly twice the diameter of the Milky Way's disk by these commonly cited values. And we should feel what that means. If our Milky Way were a city you could cross in a single lifetime, Andromeda's disk would be a city so vast that entire eras would pass before your light reached the other side. This is the scale where across stops being geography and becomes philosophy. Here's the strange advantage we have with Andromeda. We can stand outside it. We can see the disk as a shape, its spiral structure, its star-forming regions, its large-scale patterns, without being trapped inside the streets. For the Milky Way, we don't have that luxury. We live inside the disk. We measure our own home through dust lanes and partial views and indirect mapping. But with Andromeda, they can do something extraordinary. They can count. NASA describes Hubble's FAT survey, nearly 8,000 images capturing 117 million stars in Andromeda's disk across near ultraviolet, visible, and near-infrared light. That number matters because it's not poetic. It's forensic. It means we can map star populations across the disk, like neighborhoods on a grid. Young stars, older stars, star clusters, dust and gas lanes. A disk becomes readable, but then it gets stranger, because the disk is not uniform. It has structures, rings, arms, lanes like weather systems that never fully settle. In Swift's ultraviolet view, NASA emphasizes those hot, young blue stars in the disk beyond the redder bulge. Ultraviolet light doesn't favor the old and quiet. It favors youth. It favors heat. It favors the kind of stars that burn fast and die young. And in that same Swift description, NASA notes that star clusters are especially plentiful along a ring about 150,000 light-years across, a ring of activity, a giant band where star formation has been unusually rich. So the disk isn't just a disk, it's a layered record of stellar birth and stellar death, written in where young stars are concentrated and where older populations dominate. Hubble's FAT survey deepens that picture by resolving immense star fields, letting astronomers study star formation and stellar demographics across major sections of the disk. And this matters for our main mystery, scale, because the disk is where scale becomes emotionally legible, not just big, but structured, not just stars, but generations. Now we reach the part that feels like a cosmic secret. Spiral arms look like solid features, like the same arms have always been there, but the disk is rotating, shearing, grinding time into motion. So how do arms persist? One major explanation is density wave theory, developed by astronomers Chia-Chiao Lin and Frank Xu. Spiral structure can behave like a density wave pattern, regions of higher density moving through the disk rather than fixed material arms. Britannica describes Lin and Xu, showing that spiral shape can arise naturally from large-scale disturbances in a galactic disk's density, and Scientific American points to the deeper tension. There are versions of spiral theory where waves are steady and long-lived, and versions where spirals are transient, forming and dissolving over time. That tension is useful, because it means we shouldn't speak about spiral arms like carved stone. We should speak about them like weather, organized, but not permanent in the human sense, long-lived, but not frozen. And in either case, the disk becomes even more astonishing. It can produce large-scale structure, sometimes for long times, across distances that dwarf our ability to imagine. That should feel impossible, except gravity is patient, and the universe has had billions of years to organize itself. To feel a disk, we have to feel its timescales. NASA notes, it takes our Sun about 250 million years to complete one orbit around the Milky Way's center. NASA summaries place this on the order of a few hundred million years, depending on the measurement and definition. 250 million years ago on Earth, we were not building cities. We were not even close. The continents themselves were unrecognizable, fused into a single vast landmass called Pangaea. Earth was recovering from the worst mass extinction in its history, and the dinosaurs had not yet dominated the world. That's 1 year in our galactic neighborhood, one lap of the track. So when we talk about spiral structure in disks, we are not talking about quick change. We are talking about slow, enormous motion, patterns that can persist long enough to shape where gas compresses and where new stars ignite. This is why the disk is a city of stars. Not because it's crowded, but because it has districts, traffic, flow, history. You can feel the trap we live in. When you look up at the Milky Way on a dark night, it looks like a river of light, but you're not. Looking at the galaxy the way you look at Andromeda, you're looking from inside the disk, through dust, through overlapping star fields, through perspective distortions. And that means our home galaxy can feel smaller than it is, or larger than it is, depending on what we can detect. NASA's own public descriptions remind us the Milky Way's disk spans more than 100,000 light-years, but feeling that from the inside is another matter entirely. And that's why Andromeda matters so much to this story. It gives us an external reference, a second city to compare to our own, a way to calibrate our sense of scale without being trapped inside the streets. So what have we uncovered? Andromeda's disk is more than 220,000 light-years across by NASA's swift descriptions. The Milky Way's disk spans more than 100,000 light-years in NASA's summaries. Andromeda's disk contains enormous diversity, young blue stars and star clusters in the disk beyond the bulge. Hubble's FAT survey resolved 117 million stars in the disk, turning a glowing smear into a mapped population. Spiral arms point to organizing physics, density waves and/or transient patterns, where gravity and rotation shape structure over vast timescales. So the disk is not just where the stars are, it's where scale becomes visible as structure. It's where we stop thinking of a galaxy as a picture and start recognizing it as a system with memory. But that relief doesn't last, because once we accept the disk's size, another question rises, colder and more disturbing. The disk is the bright part, the part we photograph, the part we count, the part that feels like the main body. But this is where the universe quietly humiliates us again, because above and beyond that disk, surrounding it, there is more. A vast, faint component of stars that doesn't shine like the disk does. A structure so dim and most of it is invisible to ordinary images, yet so large it reshapes what galaxy even means. And that's where we go next. Because if the disk is a city, then what surrounds it is not empty countryside. It's a halo, a ghostly ocean of stars, quiet, massive, and easy to miss. And once we step into that darkness, the scale of Andromeda stops being impressive and becomes genuinely hard to live with. When we picture a galaxy, we picture what shines: a bright core, a spinning disk, spiral arms like luminous fingerprints. But then we reach the edge of that light, and we expect the story to stop, except it doesn't, because beyond Andromeda's disk, beyond the last obvious streetlight of stars, there is another structure. It doesn't glow like a galaxy. It doesn't announce itself. It surrounds the disk like a cold, quiet ocean, a stellar halo, a vast, spherical population of stars so faint we can stare straight through it and feel nothing. And what makes this disturbing is what it implies. If a galaxy can extend far beyond what we see, then our idea of size has been incomplete from the beginning. A stellar halo isn't the disk. It's not flat. It's not tidy. It's not where most star formation happens today. It's a diffuse cloud of stars surrounding the bright galaxy, an enormous volume filled with ancient populations and shredded debris from smaller galaxies that didn't survive. Astronomers describe stellar halos as repositories, places where the stellar material from a galaxy's long history of accretion gets stored. So when we talk about the halo, we're not talking about decoration, we're talking about memory. And that's when the story cracks open. If the halo is memory, then every faint star out there is a surviving witness. Imagine we're standing at the edge of a city at night. Downtown is bright, the streets are loud with light, but beyond the suburbs, the city doesn't end abruptly. It thins into scattered homes, then lone farm lights, then a few distant windows, until the land becomes so dark we can't tell if there are people there at all. The city still exists out there, we just can't see it easily. That is Andromeda's halo, the part of the galaxy that fades so far outward it becomes almost indistinguishable from the sky. Here is the problem. Halos are low surface brightness, not a little dim. Dim in the specific way that defeats human vision and even challenges large surveys. The Pan-Andromeda Archaeological Survey, PANDAS, was built around this reality. Halos are expected to extend beyond 100 kiloparsecs, and they require large area observing precisely because their light is so faint. So astronomers don't see the halo the way we see a bright galaxy photo. They extract it by counting stars, by mapping densities, by carefully subtracting the foreground noise of our own Milky Way. And that effort reveals something unsettling. The halo is not smooth, it's scarred. When astronomers mapped Andromeda's halo deeply, they found structure, streams, clumps, and substructure, evidence of past events that didn't end peacefully. In one major panoramic analysis of Andromeda's halo, researchers report that only a relatively small fraction of halo stars sit in obvious stream-like structures, but that the fraction in streams can be significant, depending on the stellar population, and they quantify stream fractions across metallicity groups. That's a quiet sentence, with violent meaning, because streams are what happens when a smaller galaxy falls in, gets torn apart, and its stars are stretched into long tidal ribbons. So the halo isn't just outside, it's evidence. It's where Andromeda keeps the remains of what it consumed. And this creates a deeper mystery. If the halo is filled with debris, how far out does this debris go? How big is the invisible sphere around the disk? This is where intuition breaks again. In that same large-scale analysis, the researchers find that the smooth halo's density profile stays close to a power law from about 30 kiloparsecs out to roughly 300 kiloparsecs. 300 kiloparsecs. That number needs translation. That's on the order of 1 million light-years across in diameter, when we're talking about a radius of 300 kiloparsecs. And even if we stay with the more conservative, frequently mapped territory, Panda's star counts and related work routinely trace Andromeda's halo out to around 150 kiloparsecs in projected radius, already close to 500,000 light-years. So the halo isn't a thin atmosphere, it's a realm, a volume so large that if Andromeda's disk is a city, the halo is the continent around it. And here's the strange part. This enormous structure is still made of ordinary stars, real light, but spread so thin the universe can hide it in plain sight. And this is the uncomfortable truth. You have never looked at a typical image of Andromeda and truly seen the halo. Most images show the bright disk and the obvious dust lanes. They feel complete. But the halo is a different kind of reality, one that exists below the thresholds our eyes evolved for. So when we think we've seen the galaxy, we've usually seen the part that shouts, not the part that whispers. Now comes a paradox that feels almost unfair. Something can be faint and still contain immense mass, because faint here doesn't mean small, it means diluted. A halo spreads stars over a staggering volume which drives surface brightness down, even if the total number of stars is enormous. In that panoramic halo analysis, researchers estimate the stellar mass in Andromeda's halo beyond a certain inner boundary as on the order of 10 billion suns, with the smoother component being several billion suns, ultimately suggesting the smooth halo could be a significant fraction of Andromeda's baryonic mass. Translated into human feeling, if we tried to account for these stars one by one, 1 second per star, we would run out of human history long before we ran out of halo. Counting 10 billion stars at 1 per second would take about 317 years of non-stop counting, longer than the United States has existed as a nation. So halos teach us a cruel lesson. The universe can store huge amounts of matter in structures that don't look like anything at all. Now we move from size to meaning. Hubble's deepest visible light work in Andromeda's halo resolved about 300,000 halo stars in a single deep field. And when astronomers examined these stars, the halo stopped being a simple, ancient leftover. They found a complicated timeline. ESA's Hubble release describes a result that feels like a warning. About 1/3 of the halo stars formed 6 to 8 billion years ago, surprisingly young for a halo population. 6 to 8 billion years ago. That is before Earth even existed, before our planet formed, before the sun stabilized into the calm star we know. So when we say young in a halo, we don't mean young like a tree, we mean young like a cosmic event. And that youth implies disturbance, mergers, accretion, a more active and chaotic history than a simple, quietly aging halo. The halo doesn't just tell us that Andromeda grew, it tells us how. And chemistry reinforces that story. In the large-scale halo analysis, researchers detect a metallicity gradient that declines outward, meaning the outer halo is more metal-poor, more chemically primitive, consistent with material added from smaller, less enriched systems. So the halo becomes a layered archive. Inner halo, more enriched, more complex. Outer halo, older chemistry, thinner populations. Streams, the visible fingerprints of things torn apart. And this is why halos matter for the true scale of the Milky Way, because Andromeda is our best external mirror. If Andromeda's visible disk is only the bright heart of the system, then our own galaxy's true extent likely lives in the same kind of faint, sprawling, hard-to-draw structure. So what have we uncovered? We've uncovered that the galaxy we admire, the disk, the spiral arms, the bright center, is not the whole organism. The halo surrounds it like a second body. It extends to hundreds of thousands of light years, and halo structure can be traced out to scales approaching hundreds of kiloparsecs in star count studies. It is extremely faint, requiring wide field surveys built specifically for low surface brightness work. and it preserves the galaxy's violent history, streams, gradients, and mixed ages that point to mergers and accretion over cosmic time. The halo is where the galaxy stops being a picture and becomes a process, a long, slow construction project built from collisions, absorption, and time. But now the universe has one more twist, because even this halo of stars, vast as it is, may not be the dominant thing surrounding Andromeda. The stellar halo is what we can barely detect, but the motions of galaxies, the way stars and satellites move, the way Andromeda holds itself together, all of it points to something larger, something we cannot see at all. And that's when the real problem appears. If the halo we can detect already reaches into the deep dark, what invisible structure must exist beyond it, with enough gravity to shape everything we've described? Because the next layer of scale isn't faint, it's invisible, and it may be the majority of the galaxy's mass. So now we step into the unsettling heart of the story: dark matter, the invisible majority. We've been chasing Andromeda by its light, a disk of stars, a halo of faint stellar ghosts. But now we reach the point where the story becomes uncomfortable, because the next layer of Andromeda is not faint, it's not dim, it's invisible, and yet it may be the largest part of the galaxy by far. This is the quiet scandal of modern astronomy. Most of what controls the galaxy does not shine, it does not glow, it does not reflect, it only pulls. And if we want the true scale of Andromeda and the true scale of the Milky Way, we have to measure a structure we cannot see by watching what it does to everything else. When astronomers say dark matter, they don't mean dark like dust. They mean dark in the strictest sense, matter that doesn't emit, absorb, or reflect light in a way we can detect. NASA puts it bluntly: dark matter is inferred through gravity, and it's thought to make up about 85% of the universe's total mass, and around 27% of the universe's total mass energy. So the universe is not mostly stars. Stars are the glitter on the surface. Dark matter is the deep structure underneath, the scaffolding that tells galaxies where to form, how to rotate, and how to stay together. But then we hit the central problem. If dark matter doesn't shine, how do we know it's there at all? We know it the way we know wind is there, not by seeing it directly, but by watching what it moves. The first major clue came from motion. Stars orbit galaxies the way planets orbit the sun. Speed depends on how much mass is inside the orbit. So astronomers measured how fast stars and gas move as you go farther from a galaxy's center, what we call a rotation curve. In the 1970s, Vera Rubin's work helped turn this into a crisis. NASA describes the core shock. Stars near the edges of galaxies move too fast to be held in orbit by the gravity of visible matter alone. And Andromeda was part of that story early. Rubin herself published a detailed spectroscopic rotation study of M31 in 1970. That observation opened a door we couldn't close, because it suggested something deeply unsettling. When we add up the mass of stars, gas, dust, everything that shines, it isn't enough, not even close. So either gravity behaves differently on galactic scales, or the galaxy is filled with a hidden mass we cannot see. And for decades, evidence across astronomy has kept pointing to the same conclusion. There is more matter than light. Picture a playground carousel at night. We can't see the metal frame clearly, but we can see the children holding on as it spins. If the carousel is light and small, it slows quickly. If it's heavy and massive, it resists slowing. It has deeper momentum, deeper pull. Now imagine we measure the speed of the children at the edge, and they're moving as if the carousel is far heavier than what we can see. That's what rotation curves do. They are the galaxy's behavior, and the behavior reveals hidden mass. Modern work doesn't just say dark matter exists, it builds dynamical models of Andromeda that include stellar mass, gas, and a dark halo, then tests whether the model reproduces what we observe. Peer-reviewed studies continue to model M31's mass distribution and dark halo using rotation curves and other constraints. That matters because this isn't one measurement. It's a repeated pattern across methods and eras. If we model only the visible components, the outer rotation doesn't make sense. If we add a dark halo, the galaxy's motion becomes explainable, and this creates a bigger problem. If dark matter is shaping the disk's rotation, then it must extend well beyond the bright disk, much farther than the last visible stars. Here's where our intuition breaks again. Astronomers describe a galaxy's dark matter envelope in terms of a virial radius, a rough boundary where the galaxy's gravity still dominates as a bound system. In modeling the Milky Way Andromeda system, researchers describe total mass distributions extending out to a virial radius of about 200 to 300 kiloparsecs. That number needs translation because kiloparsec is not a human unit. NASA's own explanations remind us 1 parsec is 3.26 light-years, and a kiloparsec is 1,000 of those, so a few hundred kiloparsecs is on the order of 1,000,000 light-years. Not the disk, not the star halo, the dark matter realm, a structure so large that light itself would need about 1,000,000 years just to cross it. And now the scale becomes emotional. While early humans were painting on cave walls, while the first cities rose and collapsed, while empires formed, fought, and disappeared, a beam of light would still be traveling across the gravitational body of a single galaxy. That is what over 1,000,000 light-years really means. And here's the quiet truth. You have looked at Andromeda and assumed you are seeing the thing itself. But the light you see, the disk, the glow, is only the bright center of a much larger system. When you look at that patch of sky, you're looking through an invisible architecture that extends far beyond the image in your mind. The galaxy you recognize is not the galaxy that controls the motion. Now we arrive at the central contradiction. If dark matter is most of the mass, why doesn't it glow? Because light is not what mass is required to do. Stars glow because nuclear fusion makes them furnaces. Gas glows because it heats and radiates. Dust reflects because it interacts with light. Dark matter, whatever it is, doesn't behave that way. NASA emphasizes that it doesn't emit, absorb, or reflect light in a detectable way. So we don't map it with a camera. We map it with consequences, with orbits, with speeds, with the way galaxies and their satellites move. And this is why Andromeda becomes so important, because it's close enough for precision, and large enough to be a full test of cosmic structure. A galaxy's dark matter halo isn't just an abstract sphere, it's a gravitational territory, and the simplest proof of territory is this. Things orbit inside it. Astronomers estimate the mass of the Milky Way and Andromeda by studying the motions of satellite galaxies, reporting enclosed mass estimates out to distances like 100, 200, and 300 kiloparsecs. More recent work continues to use satellite kinematics to estimate Andromeda's total mass within about 300 kiloparsecs. This matters because the satellites don't orbit the bright disk. They orbit the galaxy's true gravitational body, so every satellite galaxy is like a test particle dropped into the dark. Its motion is a message. This is how far the halo reaches. This is how deep the gravity well is. And the moment we accept that, the emotional graph spikes again. If Andromeda's halo is that vast, then the Milky Way's halo, our halo, likely extends into similar distances we almost never picture when we think home. So now we can say it clearly. Andromeda's true scale is not the bright disk. It's not even the faint stellar halo. It's the full gravitational system, the dark matter halo, extending out toward hundreds of kiloparsecs on the order of 1,000,000 light-years. And that changes everything about how we think of galaxies. Galaxies are not just collections of stars. They are luminous islands embedded inside invisible continents. Dark matter is the reason spiral disks can rotate the way they do. Dark matter is part of why galaxies form and cluster the way they do across the universe. And dark matter is why the size of a galaxy is never just the size of what shines. This is why the universe feels like a cosmic mystery. We live in a reality where the dominant substance doesn't announce itself with light. It shapes us silently. But the universe has one more twist. Because dark matter doesn't just surround Andromeda. Like a smooth fog, it shapes the wreckage around it. The streams, the satellites, the smaller galaxies trapped in Andromeda's gravitational territory. And that raises the next unsettling question. If Andromeda's dark halo is a vast hunting ground, what has it already captured? What smaller galaxies have wandered in and been stretched, shredded, absorbed, until their stars became part of Andromeda's outskirts? Because the next chapter isn't about a single galaxy anymore. It's about the bodies around it, a graveyard of smaller galaxies, and the tidal scars that prove Andromeda grew by eating. When we look at Andromeda, we see a spiral, a clean shape, a calm glow. But that image is a lie, only because it's incomplete, because Andromeda is not just a galaxy, it's a system, and the space around it is not empty. It's crowded with smaller galaxies, dozens of them, circling like moths around a furnace. But then, we notice something colder. Not all of them are intact. Some of them are already losing themselves, stretched into long, pale rivers of stars, tidal streams, drifting through the darkness like smoke that never disperses. And that's when the story cracks open. If Andromeda is surrounded by debris, then Andromeda has been feeding. NASA describes the Andromeda system as containing 36 dwarf satellite galaxies orbiting the main galaxy. 36. That number alone changes the feeling of the scene. We're not looking at a lone island. We're looking at a capital city with towns and villages caught inside its rule. Some satellites are famous, bright, enough to be catalogued centuries ago. NASA notes that Messier 32 is one of the 2 Messier-listed satellites of Andromeda, alongside Messier 110. But most are not bright. Most are dwarfs, small, faint, fragile. And in a universe ruled by gravity, fragile things don't stay unchanged. They get pulled, they get stretched, they get unmade. Imagine this. We're standing outside at night, watching a campfire. The flames of the main galaxy, bright, obvious, impossible to ignore, and around it, sparks lift into the air. Some sparks rise and vanish, some drift outward, but a few get caught in a looping wind, circling the fire again and again until they fade into ash. That's what Andromeda's satellites are. Small galaxies caught in a gravity field so large that escape becomes rare, and every orbit is a risk, because each pass near Andromeda is another chance to be torn apart. Our eyes weren't built for this part. A tidal stream can be so faint that even though it contains millions of stars, it barely registers against the black. To human vision, it's nothing. But telescopes don't share our limitations. In 2001, astronomers reported the discovery of a giant stream of metal-rich stars in Andromeda's halo, evidence written directly into the outskirts of the galaxy that something had been disrupted and spread out across space. ESA's Hubble team describes Andromeda's giant stellar stream as the remains of a companion galaxy torn apart by Andromeda's gravity and engulfed. That is not metaphor. That is physics. Gravity doesn't just hold galaxies together. Given time, gravity can dismantle them. One of the most prominent structures is often called the giant stellar stream. Caltech IPAC's NED review page describes it as a coherent structure traced out to a projected distance of about 100 kiloparsecs, with a width of about 25 kiloparsecs. We translate that into light years, because our minds need something they can hold. 100 kiloparsecs is roughly 326,000 light years. 25 kiloparsecs is roughly 81,000 light years. So this stream is not a small scar. It's a stellar river hundreds of thousands of light years long, wide enough to swallow the entire bright disk of many galaxies. And here's where the emotional weight lands. That stream is not an object Andromeda has. It's an object Andromeda made by tearing something else apart. A tidal stream is a memory. It's what remains when a smaller galaxy falls in, and the tidal forces stretch it like soft clay. Stars don't collide. They don't explode into dust on impact. They simply get reassigned. Their old galaxy loses its shape, and the stars become a trail, an orbit made visible, a kind of celestial handwriting, and astronomers read that handwriting to reconstruct the crime scene. Some research even argues that Andromeda may have experienced a significant merger in its past, on the order of about 2 billion years ago, with consequences that may relate to structures we still see today. 2 billion years. When that happened, Earth wasn't a world of cities or animals or even complex life as we know it. It was mostly microscopic. The planet was still learning how to breathe, and yet the stream we detect now is still there, still drifting, still refusing to disappear. Because at galactic scales, destruction is slow, and it lasts. This is the part that sounds violent, but it's ordinary. In modern cosmology, big galaxies grow by gathering smaller ones. This isn't a rare event. It's one of the main ways galaxies build their halos and reshape their disks over cosmic time. Even the language in astronomy reflects that blunt reality. Galactic cannibalism. Not as a dramatic phrase, but as a description of what gravity does when there's a large mass and a smaller mass nearby for long enough. Andromeda's tidal streams are proof that this is not theory alone. It's a record in the sky to map these faint structures. Astronomers don't look, they count. They separate Andromeda's halo stars from foreground stars in our own Milky Way. They build star count maps across huge areas of sky. They combine surveys, photometry, spectroscopy, and years of telescope time. NASA's Hubble work on Andromeda's ecosystem describes ambitious programs designed to map satellite galaxies in three-dimensional space, work that doesn't happen in a night, or a week, or even a single year. This is not casual observing. This is archaeology on a cosmic scale, except the ruins are made of stars. And then it gets stranger. Some research reports that a substantial fraction of Andromeda's satellite galaxies appear arranged in a thin, coherent plane, rather than being scattered randomly. That doesn't automatically tell us why, but it tells us something important. The outskirts of Andromeda aren't simple, they aren't smooth. They carry structure, they carry history, and that history might include group infall, tidal origins, and past interactions that still echo in where these dwarfs are today. So when we say satellites, we're not describing decoration. We're describing the living edges of a galaxy where the past is still active. And here's the uncomfortable truth. You can look up at Andromeda from a dark hillside and feel you're seeing something complete, a bright spiral in the distance. But the real Andromeda extends far beyond that glow, into a region filled with faint companions and star rivers that our eyes cannot detect. A graveyard you could stand beneath for your entire life and never know it was there. Not because it's not real, but because human vision is not built for the true aftermath of gravity. So what does this reveal about scale? It means the size of Andromeda is not only measured by its starlight, it's measured by its reach. Because wherever Andromeda's gravity dominates, it collects things. It traps dwarfs. It tears some apart into streams. It absorbs their stars into its halo. And over time, this is how a giant spiral becomes a giant spiral, not in a single creation event, but through accumulation, through capture, through quiet, repeated consumption. This is why Andromeda doesn't feel like a single object anymore. It feels like a long process, a machine running on gravity. But this raises another question. If Andromeda is surrounded by broken satellites and tidal scars, then what about us? Because the Milky Way also has dwarf companions. We also have streams, stellar crumb trails left behind by disrupted galaxies. So the next step is unavoidable. We have to compare the two great spirals of the local group, not as pretty shapes, but as predators with histories. And once we put Andromeda beside the Milky Way, the mystery sharpens. Why does Andromeda appear slightly more massive in many measures? And what does that difference mean for the kind of galaxy we live inside? That's where we go next. We keep calling Andromeda our neighbour. We picture it as the bigger house across the street, a grand spiral, glittering with 1 trillion suns, sitting out there in the dark. But here is the uncomfortable truth. When we try to compare Andromeda to the Milky Way, we're comparing a portrait to a life we can't step outside of. We can photograph Andromeda from the outside. We can trace its spiral arms like fingerprints, but we cannot do that to our own galaxy, because we are trapped inside it. We are trying to measure a cathedral while standing in the middle of the aisle, and that's where this chapter becomes a problem, because the true scale we're chasing is not just about distance, it's about perspective. It's about the fact that our home galaxy is the one thing we can never see whole, and if we can't see it whole, how can we honestly say Andromeda is bigger? How can we honestly say which one is heavier? How do we compare two giants when one of them is our entire sky? But then, the scientists did what humans always do. They built mirrors out of data, and those mirrors revealed something unsettling. Let's start with what feels simple. The Milky Way is a spiral galaxy with a disk of stars stretching a little over 100,000 light-years across. Andromeda's disk stretches over 220,000 light-years, more than twice the width by some measurements. On paper, that sounds decisive. One is a city, the other is a megacity. But this is where everything changes, because size is not one number. A galaxy has multiple sizes. There is the bright disk we can see. There is the faint outer disk that fades into nothing. There is the halo of stars, the dark matter envelope, the invisible mass that refuses to glow. So when we say Andromeda is bigger, we have to ask, bigger in light, bigger in stars, bigger in gravity? And the universe doesn't give us one clean answer. It gives us a contradiction. Because yes, Andromeda appears broader with a disk that reaches farther. And yes, Andromeda likely contains up to 1 trillion stars, while the Milky Way is often estimated in the hundreds of billions. But then, when we try to weigh them, the story gets stranger. Picture this. Imagine two enormous cities at night, seen from an airplane. One city is tightly packed, bright, dense, hard to ignore. The other is wider, but its lights are more spread out, faint neighborhoods dissolving into darkness. From above, the wider city looks bigger. But if you asked, which city has more people? You wouldn't answer by counting streetlights. You'd need traffic flow. You'd need how the roads bend, how the whole city moves. That's what galaxies are like. Light shows us the neighborhoods, but gravity reveals the population, and gravity is where the comparison starts to fracture. We grow up hearing that Andromeda is the giant, and it makes sense. It's the closest large spiral galaxy to us. It's the one we can actually photograph like a living object. So our minds fall into a trap. If we can see it clearly, it must be more knowable. But our galaxy is not transparent. Dust blocks our view. We're staring through crowded star fields. We're trying to map a spiral structure from the inside, like trying to understand a hurricane while standing in its rain. That's why astronomers lean on multiple methods: infrared surveys that pierce dust, radio maps of hydrogen gas that trace spiral arms, star counts, brightness profiles, and motion studies. And the more methods we use, the more we realize the comparison isn't clean, because Andromeda's disk may be broader, but the Milky Way may be denser in some regions, because Andromeda may have more stars overall, but the Milky Way may be converting gas into stars more actively in certain parts of its disk. And then comes the heaviest question of all: which one has more mass? Not more light, not more stars, more total mass, including the invisible, kind. And this is where the universe becomes cruel, because most of a galaxy's mass is dark matter, and dark matter does not glow, it does not announce itself, it only speaks through motion, through the way stars orbit, through the way satellite galaxies drift like drifting ash around a bonfire. Astronomers can estimate the Milky Way's total mass in the rough range of about 1 to nearly 2 trillion solar masses, meaning 1 to nearly 2 trillion times the mass of our Sun. But even that is uncertain, because we are measuring our own gravity from inside the well, and if our own weight is uncertain, then Andromeda's weight becomes a moving target too. Andromeda has long been treated as slightly more massive in many dynamical models. Some analyses of local group dynamics even find results consistent with Andromeda being the heavier partner. But then, other evidence points the other way. NASA scientists have noted that recent evidence suggests Andromeda's overall mass may in fact be less than the Milky Way's when dark matter is included. So which is it? Is Andromeda the heavyweight, or is our own galaxy the silent giant? This creates a bigger problem, because if we don't know which one is heavier, we don't fully understand the local group, we don't fully understand our future, and we don't fully understand the scale of the system we live inside. So why do we still so often hear that Andromeda is slightly more massive? Because multiple lines of evidence pull us in that direction. First, Andromeda's visible disk is larger. A broader disk often correlates with a larger reservoir of stars and a different assembly history. Second, Andromeda likely holds more stars overall. That alone suggests a larger stellar mass budget, even before we talk about dark matter. Third, local group dynamics. When scientists model the Milky Way Andromeda system and the motion of nearby galaxies, they can estimate the combined mass and infer how. It might be split between the two giants. In one major analysis of nearby galaxy motions, the combined mass of the Milky Way and Andromeda comes out to around a few trillion suns worth of mass, with a mass ratio that favors Andromeda as the heavier partner in that framework. But we have to say this clearly: none of this is a final verdict, because every mass estimate is built on assumptions, which tracers we use, globular clusters, satellite galaxies, stellar streams, how far out we define the galaxy, how we model dark matter's shape, how we account for motions we can't fully measure. That's why this comparison stays unsettled, and that uncertainty is not a weakness. It's an honest portrait of science at the edge of scale. Astronomers don't pretend the universe is neat, they admit the blur, and then they keep measuring anyway. Now step back, because the Milky Way and Andromeda are not just two names on a cosmic map. They are two versions of the same ancient idea. A spiral galaxy is not an object, it is a process. It is a long, slow negotiation between gas, stars, gravity, and time. Both galaxies have disks, both have spiral structure, both are embedded in halos of dark matter, both have swallowed smaller galaxies, both are still evolving, but their histories aren't identical. And that's the point. When we compare them, we aren't just arguing about which is bigger. We're learning what a spiral galaxy can become. Andromeda shows us what a spiral can look like when it grows wide and massive over cosmic time. The Milky Way shows us what it's like to live inside one, how structure feels from within the storm. Together, they form the most important comparison in our local universe, not because it's tidy, but because it's close enough to study in detail. and big enough to humble our instincts. And now, place yourself inside the scale. Tonight, if you look up from Earth, you are not just seeing stars, you are looking through a slice of a disk that is over 100,000 light-years wide. That means some of the light reaching your eyes began its journey before modern humans built cities, before agriculture, before we even had words for galaxy. We live inside a structure so large that our own lifetime is not a meaningful unit. We are measuring giants with instruments made by creatures who live for decades. That is the tension at the heart of this story. So where does this leave us? Andromeda appears larger in disk size. Andromeda likely holds more stars, and many models still treat it as the slightly heavier partner. But the mass comparison remains uncertain because dark matter dominates, and the edges of galaxies are not sharp. And that uncertainty is not just academic, because mass is not just a number. Mass dictates gravity. Gravity dictates motion, and motion dictates destiny. And here is the final twist. These two spiral giants are not just neighbors. They are not static. They are already moving in relation to each other, locked in a slow gravitational approach, which means the comparison we've been making is also a countdown. But then we have to ask the next question, the question that turns this from a measurement into a prophecy. How fast are we moving toward each other? And how do we even measure motion on a cosmic clock? That's where the story goes next. Andromeda looks still, a quiet smudge pinned to the sky like a stain on black glass. But that stillness is an illusion, because nothing in the universe is truly at rest. Not stars, not galaxies, not even the space between them. And here's the unsettling part. Andromeda is coming toward us. Not slowly in human terms, slowly in cosmic terms. Its light is slightly blue-shifted, meaning the galaxy is approaching along our line of sight at about 110 kilometers per second, around 68 miles per second. That is fast enough to cross a continent in minutes. Yet when we speak in the language of galaxies, it becomes a different kind of motion. A motion measured in billions of years. A countdown so long it doesn't feel like a countdown at all. But then, we learn what makes this story truly disturbing. To measure Andromeda's path, astronomers had to detect motion so tiny, it almost doesn't exist to the human mind. And once they did, the future of our galaxy stopped being a guess and became a clock. When we say Andromeda is moving toward us, we're talking about two motions at once, straight toward or away from us, measured by how its light shifts in color, sideways across the sky, measured by an almost impossible drift called proper motion. The first is easier. The second is where the universe becomes cruel, because sideways motion for something 2.5 million light-years away is so small that even a powerful telescope can stare at it and see nothing change. So astronomers had to build a method that feels like cosmic espionage. They measured Andromeda's shift by comparing its stars against the fixed background of distant galaxies, using the Hubble Space Telescope's precision over many years. This wasn't casual observation. This was patience turned into measurement. Picture this. We place a single grain of sand on the far side of a football field. Then we step back several city blocks. Then we try to notice if that grain shifts, by the width of a hair, over an entire year. That's what proper motion feels like at Andromeda's distance. The motion is real, but it's almost too small to exist inside our instincts. And yet, Hubble measured it anyway. The approach speed, about 110 kilometers per second, had been known from Doppler measurements for a long time. So for decades, the story sounded simple. Andromeda is coming. A collision is inevitable. But then the real problem appeared. If Andromeda also has a significant sideways speed, the encounter could change. A direct hit could become a glancing blow. A future merger could become a near miss, at least for a very long time. That sideways speed was the missing piece. And in 2012, NASA announced that Hubble data indicated Andromeda's sideways motion is small enough that the Milky Way is destined for a major encounter, an event predicted around 4 billion years from now. 4 billion years. We need to translate that into something we can feel. 4 billion years ago, Earth was young. Complex life had not yet written its dramatic chapters. No forests, no mammals, no human eyes to look up. That's the kind of timescale we're dealing with. And yet, in cosmic terms, that's soon. Let's anchor the speed in human terms. 110 kilometers per second is about 400,000 kilometers per hour. At this speed, you could travel from the Earth to the Moon in about 1 hour. Andromeda is doing that continuously through the cold vacuum. But here's where it gets stranger. That speed alone doesn't tell us the final outcome, because in space, direction is destiny, and direction requires measuring sideways drift, which is why the Hubble proper motion result mattered so much. 1. Doppler shift, the color of approach. This is the cleanest method. Light is a messenger. When a galaxy moves toward us, its light compresses slightly toward the blue. Andromeda's blue shift is one of the most famous in astronomy, the evidence that it's approaching us along our line of sight at roughly 110 kilometers per second. That's the first confession, but Doppler shift only gives us one dimension. It tells us toward or away. It doesn't tell us how much Andromeda is also sliding sideways across the sky. 2. Proper motion. To measure sideways motion, astronomers used Hubble to compare positions over long baselines, using background galaxies as the fixed reference frame. This is where the story becomes cinematic in the quietest way. Not explosions, not bright flares, just years of still images, and the smallest shift imaginable. From that, researchers constrained Andromeda's motion and used it to infer the future trajectory. And yet, this is science, not prophecy. The uncertainties matter. Newer analyses using Gaia data and updated modeling have continued refining Andromeda's proper motion, and the long-term outcome has become less certain than the dramatic, inevitable collision headline suggested. This is not a contradiction. This is the scientific process doing what it does, reducing ignorance slowly. NASA's 2012 Hubble release framed the encounter as a major interaction in about 4 billion years. But later work has complicated the certainty. A 2024 report in Science summarizes new simulation work, suggesting the odds may be closer to 50-50 for a direct collision within the next 10 billion years, depending on updated motions and the gravitational influence of other local group galaxies. And in 2025, Nature Astronomy published a reassessment emphasizing that there is no certainty of a Milky Way Andromeda collision, with Gaia-based proper motions used as key inputs. So, what do we do with that? We do what astronomers do. We keep the two truths together. Andromeda is approaching. The exact future path depends on tiny sideways motion and complex gravitational choreography. This is why it feels like a cosmic clock. We can hear it ticking. We just can't yet read every gear. Here's the deeper reason this chapter matters. Motion is not just movement. Motion is evidence. When we measure Andromeda's velocity vector toward us and sideways, astronomers can constrain the mass of the local group, because the gravity required to shape these orbits depends on how much mass exists in the system. This is one of the most unsettling things about the universe. We can't weigh a galaxy by putting it on a scale. We weigh it by watching how it bends the trajectories of everything around it. Galaxies reveal their mass the way a hidden mountain reveals itself in a fog, by the way rivers curve around it. So, when we measure Andromeda's motion, we're not just predicting a distant encounter. We're mapping the invisible architecture of our neighborhood. We're learning how far gravity reaches. We're learning what kind of mass, what kind of scale must exist to choreograph this slow approach. And here's the quiet punch. You're not watching this from a neutral place. We are riding inside the Milky Way at the same time, inside a rotating disk, inside a dark matter halo, inside a gravitational system that is itself moving through space. So when Andromeda approaches, it isn't approaching a stationary target, it's approaching us, and we are already in motion. The sky is not a ceiling, it's traffic. So here is what we can say without exaggeration. Andromeda is approaching the Milky Way along our line of sight at about 110 kilometers per second. Hubble measurements of proper motion allowed astronomers to constrain the sideways component and model the future trajectory. The encounter timescale is measured in billions of years, with early Hubble-based projections placing major interaction around 104 billion years. But newer studies emphasize uncertainty in whether a direct collision is guaranteed within the next 10 billion years. And most importantly, motion lets astronomers infer mass and scale, because gravity writes itself into trajectories. The universe is slow, but it is not idle. And now we arrive at a deeper discomfort, because even if the merger's exact outcome is uncertain, the approach is real. And that means something unavoidable. Every photon we see from Andromeda tonight left when our ancestors did not exist. And by the time Andromeda is close enough for the sky to change, humanity may be unrecognizable or gone. So the next question isn't just, will we collide? It's heavier than that. What does it even mean to observe a galaxy in motion when the motion unfolds on timescales that erase civilizations? Because now the story isn't only about where Andromeda is, it's about time itself. Light travel time, ancient starlight, and the brutal way scale breaks the human mind. That's where we go next. We think we understand what it means to look at something. We look at a mountain, and we believe we're seeing the mountain, whole, complete, present. But when we look at Andromeda, we're not seeing a single object in a single moment. We're seeing time stretched into a shape, because Andromeda is not only far away, it is wide, vast, layered, and light does not arrive as a unified message. It arrives like a torn letter, parts of it delayed, parts of it missing, parts of it older than everything we've ever known. And that creates a disturbing question. If light is time, then what does it mean to look at a galaxy and call it now? Andromeda sits about 2.5 million light-years away. That number is easy to say, but it's not easy to feel. A light-year isn't a time unit, it's a distance, how far light travels in a year. And when we talk about space at this scale, distance and time fuse into a single reality. NASA describes Hubble as a kind of time machine for a simple reason. Light takes time to travel, to Hubble, to our eyes, to anything. So when we see Andromeda, we are not seeing a neighbour in the present tense. We are receiving a signal that left when Earth was a different world. When the light began its journey, early humans were just beginning to exist, learning stone and fire and survival, long before cities, long before writing, long before any recorded memory. But this is where the story cracks open, because Andromeda isn't just far away. Andromeda is large enough that even within the galaxy itself, light has a long, punishing journey. Here's the strange part. We tend to imagine a galaxy like a photograph, one snapshot, one frame. But Andromeda is not a frame. It's an arena, and light has to cross it. NASA's observations describe Andromeda as so large in the sky that it spans many Hubble fields stitched across a decade of work. In that wide mosaic, astronomers resolved about 200 million stars, a thin sampling of what truly exists. Now take its scale as described in NASA imagery, roughly a few 100,000 light-years across, depending on how we define the faint edges we can actually detect. Let's translate what that means in the only unit our nervous system understands: time. If something is 200,000 light-years wide, then light needs 200,000 years to cross from one side to the other. 200,000 years. That is not a human number. That is an evolutionary number. It's the time between the earliest modern humans and us, between bone tools and space telescopes, and it means something unsettling. When we look at Andromeda, we do not see a single moment of the galaxy. We see a time gradient spread across its face. Imagine a long, dark hallway. At the far end, someone turns on a flashlight. At the near end, another flashlight turns on at the same time. Your eyes receive one beam first and the other later, not because anything changed about the flashlights, but because the hallway forces a delay. Andromeda is that hallway. Its near side and far side do not reach us with the same timestamp. They can't, because the galaxy is thick with distance in its own right, and this creates a new problem, because the Andromeda we know is the bright part, its glowing disk. But the galaxy's true body is not only the part that shines. When we say Andromeda, we tend to picture the spiral, a bright core, dust lanes, star clouds. But astronomers have mapped something else, something that barely glows at all, a halo of gas, thin and ghost-like surrounding Andromeda. NASA's Hubble work describes this gas halo as extending about 1.3 million light-years from the galaxy, and as far as 2 million light-years in some directions. That means the full influence, the true breath of the galaxy, can stretch across distances where light needs 1 million years, 2 million years, just across 2 million years. When that light began crossing Andromeda's outer halo, Earth was not civilized. We weren't farming, we weren't building temples, we weren't writing myth. We were early humans, fragile and temporary, moving through an ice age world. And yet Andromeda's halo was already there, already surrounding its stars like a cold ocean around an island. So now the question deepens. If a galaxy is so large that light takes millions of years to cross its outer regions, what does change even mean? This is why the universe feels like a paradox, because every time we look outward, we look backward. NASA explains it plainly. Light carries information, and that information arrives late. JWST's science team says it even more starkly. Distant light tells us what the universe was like long ago, because it simply couldn't arrive any faster. Andromeda is close by cosmic standards, but it is still a time capsule. We are watching a galaxy as it was 2.5 million years ago, and inside that one image, if we respect the galaxy's own size, we are receiving a smeared tapestry of different ages across its structure. Subtle, but real. This is not philosophy. This is physics. Einstein's universe has a speed limit, and everything we think of as the present is built on delayed light, delayed signals, delayed truth. And if you step outside tonight and look up, it's easy to feel like the sky is immediate, like it's happening to you in real time. But it isn't. You are standing inside a slow-moving stream of messages. Even the nearest stars are sending you ancient postcards. And Andromeda, faint and quiet, sends a message that began its journey when the first ancestors of humans were just beginning to use the earliest stone tools. And that realization should change the texture of the night sky, because it means now is not a place we look at. It's a place we live in, blindfolded by the speed of light. Here's the real reason scale breaks us. Our senses evolved for survival on a savanna. Our intuition is tuned to a day, a season, a lifetime. But galaxies operate on hundreds of thousands of years for light to cross a disk, millions of years for light to cross a halo, billions of years for histories to unfold. Our brains want sharp edges and clean moments, but galaxies don't have those. They are spread out in faint structures, woven through space, changing slowly, and we only catch them through the delayed glow of their past. This is why Andromeda can feel small in the sky, while being unimaginably vast in reality. It's why the universe can look calm while holding dynamics that are too slow for fear, too large for instinct, too deep for common sense. And this wasn't the only twist, because the biggest illusion isn't that Andromeda is far away. The biggest illusion is that the universe is fast. We think of drama as speed, explosions, collisions, sudden change, but at galactic scale, the universe is patient. Even when galaxies reshape themselves, the process is often a long rearrangement. Gravity pulling, stars orbiting, halos stirring, structures shifting like continents. The cosmos doesn't rush, it unfolds, and telescopes like Hubble and Webb are built to witness this slow truth by collecting light that left long ago, preserving earlier states of the universe like layers in stone. So the silence of space is not emptiness, it's time. Time so deep that even light is late. So we've learned something sharp. Andromeda isn't just a galaxy we can see, it is a galaxy we can only see in the past. And within its own body, light takes so long to cross that the galaxy cannot even present itself as one single now. But this creates a bigger problem, because if light is delayed across the galaxy, and if vast parts of the galaxy barely glow at all, then the largest part of Andromeda's true scale might not be what we see. It might be what we can't. And that brings us to the final, unavoidable question. When we say we understand the size of a galaxy, what exactly are we measuring? Because the true scale of Andromeda isn't only starlight, it's the invisible structure that holds the system together over time. And that's where the story ends, and where it becomes something heavier. We keep calling Andromeda a galaxy, a neat word, a single object, a thing we can point to. But what we're really seeing is a mask. Because Andromeda is not just large, it is so large that most of it doesn't announce itself with light. It hides, quietly, inside darkness. NASA places Andromeda at about 2.5 million light-years away, and NASA also notes it spans roughly 220,000 light-years across. Those numbers are not trivia, they are an accusation, because if something can be that vast and still appear as a small patch in our sky, then our instincts about reality are already broken. And this is where everything changes, because the true scale isn't only about size, it's about what size does to meaning, to time, to certainty. Scale sounds like a ruler, but in astronomy, scale is closer to a threshold, a line between what we can detect and what still exists when detection fails. NASA's Hubble teams have built enormous mosaics of Andromeda, projects that take years, because even one neighbouring galaxy is too big to capture in a single glance. And in those observations, the facts become unsettling. Andromeda's total star population is estimated to be around 1 trillion stars, with many falling below what Hubble can easily detect. So even when we point one of humanity's sharpest eyes at it, the galaxy still has parts that slip beneath the floor of our instruments. Here is the strange part. If a galaxy can contain 1 trillion suns, and we can still miss countless ones, then the boundary of a galaxy is not a clean edge, it's a fading, a slow surrender into darkness. Imagine we're standing in a city at night. The downtown is blazing, streetlights, signs, windows. That's the part we notice first. But the city doesn't end where the lights end. Beyond downtown there are suburbs, dimmer streets, then quiet neighbourhoods, then roads with only a few porch lights, then long stretches where the city still exists. But you can't see it from where you stand. That's what brightness does in astronomy. It convinces us the city ends where the glow ends. But the true city is still there. Andromeda's bright, visible structure is enormous by human standards, but in cosmic terms, that bright disk is only the beginning, because there's something wrapped around it, something that doesn't shine like stars. In 2020, scientists using NASA's Hubble Space Telescope mapped a giant halo of gas around Andromeda, diffuse plasma so faint it's practically invisible, extending about 1.3 million light-years from the galaxy, and as far as 2 million light-years in some directions. Let's stay honest about what that means. A halo reaching 1.3 million light-years is more than just big. It's a structure so large that it stretches a significant fraction of the distance between Andromeda and us. So when we talk about the size of Andromeda, we have to choose what we mean. The bright disk our eyes romanticize, the faint outskirts our best telescopes chase, or the vast, ghostly envelope of gas that barely glows at all. And suddenly, galaxy stops sounding like an object. It starts sounding like a system, a layered ecosystem of stars, gas, and structure, sprawling far beyond what the night sky admits. And then the universe delivers its sharpest insult. Even all of that light is not the majority of what's there. NASA states that dark matter makes up most of the mass in galaxies and galaxy clusters. In other words, the part we can see is not the bulk of the thing. And for our own galaxy, NASA's Hubble and Gaia investigations describe a Milky Way, where only a tiny fraction of its mass is in stars. Most of the rest is dark matter, acting like scaffolding that holds the galaxy together. So scale isn't just distance and diameter. Scale is also this. The universe can be dominated by something we cannot see directly, and still behave with precise, measurable gravity. That is the kind of reality Einstein's physics prepared us for. A universe governed by what mass does, not by what it looks like. And it creates a deeper mystery. If most of a galaxy is invisible, what does it mean to say we know a galaxy at all? NASA notes our Milky Way is about 100,000 light-years across and likely contains 100 to 400 billion stars. That already sounds beyond comprehension. But then Andromeda enters the frame at about 220,000 light-years wide. We don't need to force drama here. The drama is automatic. Because once we place those numbers side by side, we feel it. Our galaxy, our entire stellar home, can be mentally held as a disk. Andromeda stretches that mental model until it thins and breaks. It tells us something uncomfortable. We are not living inside a big place. We are living inside one example of a common cosmic architecture. Spiral galaxies shaped by gravity, embedded in halos, evolving over billions of years. And the only reason it feels manageable is because we can't see the full outline at once. For years, popular science treated the Milky Way Andromeda merger as destiny. NASA even published a famous 2012 Hubble-based visualization that described a head-on collision in about 4 billion years. But science doesn't protect our favorite narratives, it corrects them. In June 2025, NASA ESA Hubble reporting emphasized that using updated data from Hubble and ESA's Gaia, there is only a 50-50 chance the Milky Way and Andromeda will collide within the next 10 billion years. A peer-reviewed Nature Astronomy paper by Sawala and collaborators echoes that uncertainty, roughly a 50% probability of no merger over the next 10 billion years, given current uncertainties and the influence of other galaxies. So even at the scale of galaxies, where time is measured in billions of years, certainty still collapses. And that matters, because it teaches us what scale really does. Scale doesn't just humble us with size. Scale humbles us with limits. Limits of measurement, limits of prediction, limits of human intuition. Andromeda is not just the next big galaxy. It is a mirror that shows us what galaxies truly are, not islands of stars, not clean disks spinning in emptiness, but evolving structures built through gravity, shaped by invisible mass, wrapped in gas, and populated by stars we can't even fully count. When we say Andromeda is incomprehensibly vast, we're not trying to sound poetic. we're describing a measurable reality that refuses to fit into the human brain. 2.5 million light-years away, meaning we see it in deep time. 20,000 light-years wide, meaning even one galaxy is a continent of time and distance. A gas halo extending 1.3 million light-years, meaning the edge is not where the light ends. Mass dominated by dark matter, meaning the visible is not the main event. This is why scale changes meaning. It forces us to accept that we live inside a universe where the most important structures are partly hidden, and where our senses are not reliable judges of what exists. If you ever find Andromeda with your naked eye, just that faint, quiet smudge, you're not seeing a small thing. You're seeing the part of a colossal system that happens to be bright enough to reach you. And what should unsettle you is this: the sky is full of realities like that. Enormous, physical, measurable, but visually subtle, almost polite. So where does this leave us? It leaves us inside a galaxy that feels like home, until we remember its width is measured in tens of thousands of light years. It leaves us next to a neighbor whose bright body is vast, whose halo is larger than our instincts allow, and whose mass is shaped by darkness we cannot hold in our hands. And it leaves us with a humbler definition of knowledge, because in the universe, certainty is expensive. It must be purchased with instruments, years, cross-checks, and patience. And even then, the cosmos keeps a margin of uncertainty, not as a flaw, but as a reminder of what we are. We are not built to feel a million light years. We are built to feel a cold wind on our skin, the weight of a quiet night, the distance between two lights on a distant road. And yet, we can still learn, we can still measure, we can still reach outward with minds that evolved on one small planet and discover that galaxies are not objects. They are long, slow histories, written in stars, gas, and invisible scaffolding, unfolding through time. And maybe that's the real meaning of scale. Not that it makes us small, but that it makes our certainty smaller. And in that shrinking, there is clarity, because the universe is not asking us to be comfortable, it is asking us to be honest, and to keep looking even when the truth is too large to fit inside a single glance.